Every single day, a modern enterprise generates millions of individual data points. Inventory adjustments, payroll hours, vendor invoices, and customer payments pour into the organization in a relentless, chaotic stream. This diagram illustrates how companies historically attempted to manage this volume using stovepipe systems. These are single-function structures designed with a strictly limited departmental focus. A transaction goes into the sales silo, and it stays in the sales silo. Because these systems operate in isolation, they force the organization to duplicate records. The marketing department and the accounting department might both maintain separate files for the exact same customer. This structural separation results in redundant entries and inconsistent data across the firm. To solve this, corporations adopt Enterprise Resource Planning, or ERP. In an ERP environment, those isolated silos are dismantled and replaced by a system that actively links multiple cross-functional business activities. By consolidating these functions into a single architecture, an ERP propagates a single data entry across every department in the organization simultaneously. To understand how a fully integrated ERP actually functions, we have to examine its underlying architecture. We need to build the system from the ground up, starting with the accounting information layer. A business cannot achieve operational visibility by patching together fragmented databases. Visibility requires a strictly integrated structural hierarchy that processes raw inputs logically from the bottom to the top. At the bottom of this hierarchy is the bedrock layer, the Transaction Processing System, or TPS. Every piece of financial data originates here. The TPS has a highly specific mandate. It is designed to handle only the routine, structured transactions required to conduct daily business. 5 core cycles feed this processor. First, credit sales and amounts due from customers. Second, cash collections from receivables. Third, purchases on credit and recognizing supplier payables. Fourth, cash disbursements for trade payables. Fifth, paying employees and allocating labor costs. The TPS relies on one overriding structural directive. It must maintain strict system integrity at the exact moment of data entry. It achieves this through an absolute rule. Transactions processed by the TPS must succeed completely as a whole, or fail as a whole. There is no such thing as a partially recorded event. If a transaction fails to meet all required parameters, the system rejects it entirely. Without this all-or-nothing filtering mechanism at the bedrock level, upstream financial reports would be corrupted by partial or incomplete records. Validated TPS data enters the accounting information system, splitting into 2 pipelines. First, the general ledger focuses on external parties, generating formal financial statements. Second, the management reporting system uses cost accounting to provide operational tools for internal strategic management. Notice the distinction between these 2 tracks. The general ledger pipeline is strictly historical and externally focused. The management reporting pipeline is forward-looking and internally focused. The accounting information system acts as the translation layer. It systematically converts raw transaction volume into both legally mandated external compliance and internal strategic intelligence. Structurally, the accounting information system operates as a specific functional node within a significantly broader framework. This is the management information system. It receives TPS input and aggregates data across the value chain. It integrates finance with manufacturing for production planning, connects logistics with marketing forecasts, and factors in human resources data like projected payroll. By connecting these separate departments, the MIS reports this cross-functional data in an aggregated format specifically designed for middle management decision-making. The transition from simple accounting to enterprise-wide planning occurs at the interface where AIS financial rigor meets the operational metrics of the broader MIS. This brings us to a structural question. How exactly does this integrated network maintain consistency across so many different departments without reverting to redundant data silos? The mechanical solution sits directly beneath the software layer, the relational database. This architecture organizes data conceptually. Data items are stored in columns, called fields. Related fields form a row, called a record. A collection of records forms a table. The mechanism that eliminates redundancy here is the key field. Instead of copying a customer's address into both the sales table and the shipping table, the database simply links the 2 tables using a shared unique identifier. Because every record has a key field that uniquely identifies it, disparate tables can be joined dynamically, on demand, without duplicating the underlying data. To navigate this grid, systems typically use Structured Query Language, or SQL. SQL allows users to execute highly specific searches, like finding every customer who ordered a specific part, without consuming massive amounts of computing overhead. Relational linking via key fields is the mathematical reason modern enterprise systems can achieve integration without the massive inconsistencies that plagued legacy systems. However, there is a critical distinction to make. The relational structure we just examined is static. The database alone is just a storage arrangement. It requires an active, operating layer to function securely. That operating layer is the Database Management System, or DBMS. This is the integrated set of computer programs that runs the database. The DBMS performs all the active duties. It creates and maintains the elements, processes the updates from the transaction layer, and safeguards the raw data from loss or destruction. It also controls user access. Based on an employee's specific role and responsibilities, the DBMS limits their access to certain data fields or logical views, enforcing strict internal security. Architecturally, the DBMS provides a common language. This allows programmers to design and code front-end applications independently of the database's technical structure. Naturally, these capabilities carry high costs. Operating a DBMS requires direct access hardware, expensive software licenses, strict security controls, and trained database administrators. And as organizations scale, the data doesn't necessarily stay in one place. It often becomes a distributed database, stored across 2 or more physical sites using replication or partitioning techniques. The DBMS provides the active processing layer necessary for company-wide integration, while its access controls prevent the systemic corruption that occurs in unstructured environments.